跟他说的也太好奇。啊，也不是每天都过来学校，偶尔来一下也是可以。哎呦，哦，这个放纵，哎，这个对，都然后下一个，这个，哦，吃饭了，是，很 fancy，它这种，对啊，它这个绿色的那个模糊的光源，刚是那种，然后那个的会，是不是很 fancy？又看到，哦，哦，哦，不可以，我我我个人这么想说，我个人的话，不是的，对，就没人问我要，我就不发了。我15号在做 slide，16号整，我还没，就没人问我要，我不知道他怎么，反正我到时候带 U 盘是可以的。 是在 speak launch 上，我不知道。每天都排了一天13个半，很高兴。哦，不高兴。对呀、这是我想示范给你。哦，我走。想试。对对，那个就是经常控制不知道。哎呀，这方面没关系，反正我吃的。啊，看你也跑的很基本。你也是活动的学生吗？哦，是的，哦，对，国二，国二，你是国4了？对。哦，这个我们一分。哦，一分钟一个。然后到我一天。
Yeah. Yeah, so I think that's the and I think yeah. The CDS have the same thing or not? It's the same. Yeah. So that's for all patients now? Or when I had a seminar at then also had this so other departments do. Yeah.
我没注册吧？记得这个册就签个字写，也是吧？这个是的话，哦，我就是这个是。看来是这个，我知道能词，做别那个，对。
Okay, good morning, everyone. So welcome to IDS, so the Institute of the Data Science. So as you may know, so the IDS is an interdisciplinary institute, and we have more than 10 professors, so coming from different areas or multidisciplinary areas, so including AI and including medicine and including Boris is law, right? Okay, so we have many so very strong professors from IDS. So and we also regularly organize seminars from outside Hong Kong or inside Hong Kong or inside IDS. And today, so it's Jinhong's turn. So he's a new professor of IDS, although he's not that new. Okay, so actually 7 months passed. So anyway, so today, so we welcome Professor Jinhong Du, okay, assistant professor from IDS, Institute of Data Science, and he will deliver a talk. So with the title is Disentangled Feature in Potency. So for Professor Du, he just joined Hong Kong U, joined IDS in this September. So as assistant professor and the framework of Hong Kong U 100 framework. And as you may know, so this framework is mainly for those outstanding young researchers. And Jinhong actually hold a joint position from IDS and also CDS. Perhaps you may know that, especially Department of Statistics and Actuarial Science. And okay, Jinhong's research actually bring the statistical theories and some high impact applications. So it's mainly for causal inference and statistics. And Jinhong actually has published many papers at top journals from statistics, say GSR, GRSD, some top conference from AI and machine learning, say the neural nets and ICML, and also some journals say the PNAS. Okay, and Jinhong actually earned the PhD in both in statistics and machine learning for CMU, and just graduated this year, and then immediately joined Hong Kong U. And let's welcome Jinhong to give us talk.
Thank you for the introduction. So I'm very happy to share with you this this talk is about some of my recent research on feature importance. So yeah, so I guess not every people know what is feature importance, but you may hear about this. So at the beginning of this slide of this talk, I will tell you a little bit about feature importance and what they are lacking. So in fact, there are different notions of importance that you can define. For instance, you can look at a local feature importance, meaning that yeah, so as you may define the importance for a feature in different ways. You can look at the importance of feature for one particular input. So in this sense, this will be a local feature importance measure, or you can call it as an individual. And on the other hand, you can also try to define the importance by looking at the population, by averaging the effects across all observations. So that will give you a probably more reliable quantification of feature importance. On the other aspects, we can also try to define the importance that related to a specific model. For instance, if you consider a linear model, then the coefficient can be viewed as the magnitude can be viewed as the importance for that specific feature. Or we can also try to define the importance for more general models in an agnostic way. So in that case, the feature importance can be applied to any black box model, and you can know which feature can drive the prediction for that model. So for this talk, I will mainly focus on the global feature importance and looking at the model agnostic feature importance. So to give you an example, so here if you have a black box model that takes 4 features, the age, the sex, blood pressure, BMI, and also an intercept of basically of 0.1 getting a disease. The model predicts that you get like 40% of probability getting a disease. So what we want to achieve with the feature importance score is to assign each feature a value. And this value can indicate how this feature change or impact the output of this black box model. So for this example, you may see that the age and sex have like 0.3 and 0.4 importance score. So compared with the remaining 2 features, you can believe that these 2 are more important. Right. So there are different application scenarios you can utilize the importance score. For instance, if you ask GPT that I know many people who are Russian, and if it complete a sentence with they love their vodka, and we want to look back to see what input tokens may make the model predict this output token vodka, and you can see that the input token Russian takes the largest value for the importance score compared to all the remaining tokens, which just have a small impact. So for this example, we can somehow expect that the model may make this prediction because of this input token Russian. Right. So
you may explain a little bit of vodka. What is vodka?
Is anyone like don't know a vodka? It's just an alcohol that
okay. Okay.
right. So because we know that
Yeah.
the Russian has made many names in Russian like drinks. They have a high correlation. Yeah, and in the other example, like in computer vision, if you have a image classifier that you for like ImageNet or some other model, you input image as your feature X, and we try to predict its classes. So in this slide, I show 3 examples. So you have 3 image, and the first column of this image will be the true classes for this image. We can try to use the importance score and assign each pixel an importance score, and you can see that this region, the bit have a largest importance score. So this can be a wide model makes prediction. And when we look at those other classes, the top 2 and to the top 4 predicted classes, you can see the very similar pattern. And all these can be used to explain why the model makes such a prediction. And similar phenomenon can be observed in other cases, like for the speedball, for the park image. Yeah, so other than these NLP and CV tasks, in more other domains like biomedical research, feature importance score such as Shapley value has been used extensively in recent research. So the reason is that researchers are start using more complicated models like random forests or neural networks in their for scientific research, and it is hard to explain what the back box model doing. So what we can do is try to assign the importance for the feature for a given prediction model and try to see what drives the prediction. Right, so there are different application scenarios for feature importance. These are very good, and there are in fact many methods proposed. So, but one question is that are they perfect? Of course not, but in different there have 2 limitations. In the first limitation, if you consider the case, if you have one prediction model fixed, but you have different data to evaluate the importance score, you may get a very different estimate for the importance score. Say if when you have 500 samples, you rank the feature importance like age, blood pressure, and BMI. But when you increase the sample size or you use another data set, you may get the rank for age and blood pressure free. So in this case, which ranking should you trust? This is one limitation of this feature importance method. And another is that if you have many features, then most likely each feature can only contribute mildly to the prediction. So in this case, you may get a feature importance score have a very small scale. So the scale may not be meaningful in some way. And compared to the importance score, you get you see from the right hand side, you have more than 0.3. So in this case, can you trust that these features are important or not? So what lacking here, the common cause for these 2 issues was they do not provide you uncertainty. So suppose you know that the first 2 features may have a larger variability, and the last one have a very narrow confidence interval, then we can conclude that at least we know the 3rd feature will be the least important, but we may not have sufficient information to know whether age or blood pressure is more important. And on the second cases, if we know that the first feature has more narrow confidence interval, then we can see that this one must be more important compared to the remaining one, which has a lower bound very close to 0. And so these are the limitation, the first limitation that we want to address in this talk. So there are some tools, standard tools in machine learning and statistics that can actually provide uncertainty quantification. But these are very basic building blocks that we will look into in this talk. So consider a setting where you have a feature X and response Y. The way we quantify the performance of a model, and here we fix this model, we treat it as a fix, as it can be arbitrary. So if we input X, the feature, it can predict return a prediction. So we can quantify its performance using a risk, the expected loss, comparing the ground truth Y and the prediction FX. So the first tool you can use is called local, the one covariate loss. So if you want to measure the importance for the XJ, the J's feature, you can compute the risk difference of a submodel where you just draw the J's feature, fit a submodel using the same algorithm. And this, because you ignore some information, the prediction will get worse. The increment can be used to quantify the effect or the importance of the J's feature. And another way to compute the importance is called conditional permutation importance. For this method, instead of dropping the J's covariate, we can consider resample of permuting the J's covariate so that to remove the information. Yeah, so it's defined similarly, but you now can use the same prediction model. So you can avoid repeating a submodel. There are other tools called traffic value from game theory. So in fact, it is you can write it as a weighted average of the local estimate and over all possible subset of the feature. So for this tool, we can do confidence interval, but it will be generally computationally inefficient. So for this talk, I will mainly focus on the first two tools, and I will because they serve the basic building blocks for this one, and in fact they all share the same another limitation that I will show you in the next slide. So why they may be like so they also face another limitation. So if we consider a linear model, that the response is just a function, the summation of two features x1 and x2. And if you compute the importance score using local or CPI, what you get will be importance that pretty low, close to 0. And the issue here is not because we assume a linear model. The issue is more fundamental. Even the model is nonlinear, even though x1 and x2 may be nonlinearly dependent, we still have the same issue. So why does this happen? This happens because we know that the two features are very correlated. So if you remove one of them, or if you permute one of them, the other one still care over some information for predicting the response. And for this reason, this is an issue we call correlation distortion, or because of their dependencies, you will get a score that is very close to 0. Right, so this issue is certainly more fundamental, because if you have a score, if you have correlated feature, you get a score close to 0, and this important score will be biased. And even in this case, the uncertainty quantification will not help. So for this talk, we will try to address these two issues. But first, looking at how can we deal with the correlation distortion issue, and then how can we quantify the uncertainty? Right, so the method we propose is called a disentangled feature importance, and the idea is very simple. So consider the case where the features are correlated. The simplest case is the 2D multivariate Gaussian. And the correlations is captured by the covariance matrix C. And in the density will look like ellipse. And this is not ideal. What we really like is something look like isotropic, where the covariance will be identity or diagonal. And how can we achieve this? In this case, it's quite simple. You just do a linear transformation, map the original feature to the latent space by decorrelation. So you multiply by covariance inverse the square root so that you can get the z. And for some more flexible, more complicated feature distribution, you can use other tools like monotone optimal transform or normalizing form to transport this continuous data. And for discrete data, you need to use some regularized one. Still, even though they may not give you a unique optimal transform map, but there are ways for you to make the features look like isotropic. Right, and this is the first step, but after this step, we get some features that have really nice property. So we can try to define the importance score for the latent function. So we just to simplify the problem, we consider the alpha log for this moment. In this case, you can define the latent feature importance as the variance of the prediction effects given all the remaining coordinate Gj. This is the importance for the J latent feature. So because of the latent features are independent, there are nice property for this quantity. So in fact, you can show that this importance score will coincide with the local and the CPI definition for the latent feature. So just to remind you, the local estimator will estimate will be the difference of the submodel rates and the original rates. The CPI will be the rates when you preview the J's coordinate and compare that with the original rates. But one subtlety here is that these importance score are defined for the latent variable. They are not defined for the original variable. So they are defined for this function, the composite function of f and the inverse transform. And this is not the target that we want to look at. And because of the independent property, it's also easier for us to estimate this importance score. Because you can just resample the J's coordinate, you can avoid submodel repeating in local. You can also avoid conditional permutation as in the CPI, because in the latent space, everything's independent. Right, so the next question is that once we have this latent importance score, how can we get back to the original space and to assign a score to the original feature X? So think about how did we get Z? We use an optimal transform map from X. So we can also get back X from Z using the inverse transform map. So the way we define it is to aggregate the importance of the all latent coordinates and by doing a weighted summation. Here the weight will be the Jacobian, the square Jacobian of the inverse transform map. And then we sum up for all the latent coordinates. And this will be the importance score we define for the XL, the L's coordinate of the feature. So you may wonder, like, why does this definition make sense? And we also think about this. And the first thing we think about this problem is that, so no matter what notions of importance we define, and this should work for linear models. So we indeed look at a special case of linear model. If you have a response generated as the linear function of X with some additive noise, and X has a covariance sigma, then we find that in a very old paper, there is a classical result for the composition of R squared. So it can show that the R squared under this is a linear model. can be written as the summation of some quantity. And this quantity, in fact, corresponds to how we define the importance for the latent feature, for the decorated features. And you can also write slightly differently, so that you have two summation, but the inner summation will correspond to how we define the importance for the original feature with some weightage. Yeah, so this also justify that why this definition for the original feature makes sense. But we propose a non-parametric extension that make it work for more than not just linear model. Okay, so once we have this definition for the importance score, the question is that how can we estimate? As I mentioned earlier, because in the latent space we can do resampling of the J's coordinate from standard normal. So we can just do a bunch of Monte Carlo samples by permuting or resampling the J's coordinate for k from 1 to n, and then we estimate the rates using n sample, and then we finally aggregate the estimate from all latent coordinates. For the Jacobian, you can just also use the empirical Jacobian to estimate it. And one more thing that I do not have time to talk into in detail for this talk would be the uncertainty quantification part. We have an estimator. What we can show is that the estimator will approach the estimate in the limit with some variance that we can quantify. And these are based on a semi-parametric inference theory, but I will not get into the detail. The main message here is that once you have a limiting distribution, you can somehow estimate the variability of your estimator, and that will give you uncertainty quantification in finite set. Okay, so there are in fact different ways that you can further extend our proposal. So I introduced that for the L2 loss. You can do it for more general losses by, if you recall that the definition, it in fact can be written as the difference of rates. Then I can just replace the L2 loss by arbitrary loss. And then I substitute this formula back to the inner summation or inner expectation. And this will give rise to the future importance score for arbitrary loss. And we can still quantify the uncertainty for this quantity. The second extension is that we can replace the second component, how we measure the sensitivity or the weights by using more flexible form matching method. Right, and after this, we call this an extension as a full disentangled feature importance, and we will see some performance with respect to the previous version of Gaussian optimal transport in the simulation and real data. Okay. So next I will show you some simulation study. We have a lot in the paper, but here I'll just show you one so that you can get the main message from this simulation study. So consider when we have a nonlinear model, which is very complicated, the outcome y is a function of y feature x0 to x4. And this function is, of course, nonlinear and non-smooth because of the step function. We have more than 5 features. We have totally 50 features, and the features are correlated, where the correlation structure can be shown in the heat maps. As you see, there are 5 blocks of in this correlation heat map, and each block have 10 features. So in other words, you can think of in this setting, there are 3 subsets of features. The first 5 features are those active features that generate the response. The second set of features are those features that may not be used to directly generate the response, but they still carry over the information because they are correlated with the first set of features. And the remaining 40 features will be those null. And we can see whether the methods will make like for discovery of these features. And we pick mandatory on this simulation. So just to give you the final result, we consider for measure the local CPI as we introduced before, and also there are different versions of both disentangled feature importance and the original one with a Gaussian optimal transform. If you look at the AUC on the first and the last set features, all the methods are doing good, and the Taiwan errors are good because these methods all have alternative quantification that can guarantee the Taiwan errors are well controlled. But the most interesting thing is the power. See, when you look at the power of the active features, the local and CPI will have a pretty low power. But of course, as sample size increasing, then we will get also high power. The reason is that when you have corrective features, their estimate will be biased towards zero. So you get less discoveries using the local and CPI in the presence of correlation. And if you consider both the first and the second set of features, similar issue happen. And so in the second law of this talk, I vary the correlation strength. So for the AUC and the Taiwan error, the results are similar. But what's interesting is for the power. If the correlation strength is increasing, local and CPI will get a smaller power. On the other hand, the bulk or this disentangled feature importance of variance will get a higher power because they can utilize this correlation structure to make a better alignment. Right, so we can see that if the features are truly correlated, then we should not rely on the local CPI as they will be give you a bias influence. So at the last part of this talk, I'll show you one real data study that how do we really use this importance score on some fundamental data. So in this data, these are some CDG data set. The raw data looks like a time series fetal heart rate data, and based on this data, the doctor or in their view, they have a way to extract some features from this time series data. For example, you can count the baseline counts, and you can count how many the number of deceleration, or you can look at the variability of the histogram statistic from this time series data. And then eventually we get 21 continuous features. The sample size is like 2,000. For this data set, our goal is to pick a classifier to see whether for a given records or whether the fetal state is normal or abnormal. So this is a binary classification problem with 21 continuous features, and we use our random forest to do this. So the first thing we do is to inspect the feature structure. And as you can see, if we compute the Schiemann correlation matrix here, here the row will correspond to the column. So you will see that this first row will be the same as the first column, the baseline. And you can see a graph structure for the first four features, the baseline, mean, mode, and median. And in the middle, there are also another very apparent blocks for some variability statistic. So the feature here is because they are all constructed from the time series data. They are very highly correlated. Now, if we apply different method, the local CPI on this data set, what we find is that the final estimated score from CPI and local will be very small. And only two or three of the features are things to be important. And for our methods, only one of the features that are insignificant. And when we take a look at this feature, we plot a histogram of this feature D as a short number of severe deceleration per second. We see that for the individuals who have abnormal state, they only have 7 observations. So maybe at least for these features, there are not enough data under positive class to make the classifier predict well. So the classifier may not rely on this information. Yeah, and so in this case, you can see we can achieve a higher power because we hypothetically we know this feature should more or less contribute to the prediction for the doctor to decide whether this person have an abnormal fetal state or not. And another thing is that you can use the ranking to pick the top K important features. So just to give you an example, how can we compute the feature importance score for the original feature from the latent important feature? So in fact, in the latent space, not many features are highly important. Many of them has a score that are close to 0. So this also suggests that the feature you have has a slightly low intrinsic dimension, but after the assignment, the attribution using the Jacobian matrix, we can get a more reliable quantification for the importance score of the original feature X. Right, and you can also see certain block structure of the Jacobian we estimated for the data. Yeah, so there in machine learning community, there in fact another way that people may commonly use to deal with correlation. What they do is that they can first put a hierarchical clustering on the features, and then they choose a arbitrary cutoff to split the features into different classes. For each classes, each cluster, they can just retain one feature as the cluster representative feature. For the remaining cluster representative features, of course, the correlation will get reduced. But the question is that whether it is a good way to deal with correlation. So in fact, we show that if you do it in that way, you will get a drop of accuracy because you remove some of the information that the model can utilize. So we suggest that if possible, you should not do this ad hoc method to reduce the number of features. Right. So we also have tried on many other data, including some biomedical or industrial data sets, but for the time, I will not go into this detail. And at the end of this talk, I'll just give a summary of what this talk is about. So all this talk is motivated by 2 limitations of the current feature importance method. One is that many of them are sensitive to correlation. If you have a high correlation in the features, the importance score you get will be biased towards 0. And for many of the Apple feature importance score you may see, they may not give you uncertainty, so that you may not know whether we can trust, how much we can trust this importance score. So to address these 2 limitations, what we propose is to first disentangle the features into a latent space, assign latent importance score, and then attribute back to the original feature according to the Jacobian or the correlation structure. And we have seen some improvement over the real data and simulation study. Yeah, so mostly this is about the talks, and yeah, so this will be the end of the talk. And the other talk is from two other papers. the first it would be a paper that more statistical theory, more statistical theory, and the second paper will be an extension of the previous one that we have applied on some of real data case studies. Yeah, so I will stop here and to see if anyone has questions.
Questions? Can we start with the offline?
Thank you.
I just put everyone. Let's start with the
Okay. Yeah, I can just show. Okay, thanks a lot, Jinhong, for the talk. So what I'm gonna ask you is about, because you mentioned you need to learn the mapping T, right? And there's a mapping T, if you have relative high dimensions, the mapping T cannot be learned perfectly. So my question is gonna be two. First is, how does the master is sensitive to the quality of the learned mapping? Like if the mapping is not very good, does it affect the result? And second is, you mentioned asymptotic normality. Is this based on the true mapping or is based on empirical mapping? And if it's empirical mapping, how does it affect the result?
Thank you for the question. So for the first one, yeah, of course, the result depends on the how accuracy the accuracy of the transform map you estimate. For the first part, if you use a Gaussian optimal transform, in fact, this can be efficient and accurate if the data somehow continuous and look like if the distribution is not too weird. And for the second one, that one would depends on how much of the data you have to train the pro matching. Right. So yeah, for the first question, of course, the accuracy will depends on the transform map. And for the second question, the asymptotic normality will also depends on the accuracy for the transform map. And for the theory, we just need to assume that it has a certain rate. But in fact, for empirical purpose, you can always find more features without label to include the estimation of the transform map, because this that does not require the label. And for unlabeled data, it will be you may have a larger amount, so the convergence we will get better in that case.
Thank you very much. So it seems like I can just do PCA, disentangle all the features, rather than using this kind of Jacobian, because you have to learn how to transform the data to disentangle them, right? The PCA automatically will do this.
Yeah, this is a very good question. So again, we come back to the motivation. So why we want to do this? Because we always train the predictor, the prediction model this. As when after you have the model, you want to expand that. How can you do that? And this is our motivation. So if I go to the definition, yeah, so we always treat the prediction model to be fixed, and you have access to this model. But other than that, you do not know too much about it. So we want to avoid repeating of this model.
More question?
Thanks for the talk. I wonder whether the proposed method is robust to highly correlated data, because just suppose that X1 and X2 are highly correlated Gaussian, and then you need a transform map that involves the inverse of the correlation matrix. But when it is highly correlated, would the error of approximating or estimating this precision matrix get very big, such that the latent feature map would be distorted because of this correlation?
That's a very good question. So if the two features are exactly the same, then of course you cannot do that.
But what if they're just highly correlated, like a very
But whenever they have some noise and the noise strength is not go to zero, then you can still do this.
Oh,
Right. But it will need some variations. So
thank you for this nice talk. So, I noticed that in your real data analysis, you conducted analysis on TCGA and some single cell data. So, I'm wondering whether computation can be a problem in your method, because in TCGA there's a large number of SNPs, and it seems that for each like for each feature, you need to construct this map, and because they will have lots of features, then you should construct mapping for like a large number of times. Yeah.
right. So the map is constructed for all the features at the same time. So you only need to do it once. But yes, your concern is it's very the dimension are large, then it may be hard to train a full matching. But in some cases it depends on your motivation. If you have a black box model that you do not want to retrain, then the only thing you can do is to explore the feature structure and to calculate the concordance law. And if maybe you need to trade off that if the black box model is easier to retrain or repeat, then obviously you can do that. But in most cases, if these are neural networks, then most likely doing the way that I suggest may be more durable.
Oh, thank you for your talk. So I'm curious whether the feature importance map is related to the attention map. So they both seems to highlight the region that the model emphasizes. So I'm wondering if there's any conceptual or methodological connection between them. Thank you.
Where we have this feature importance for. Yeah, so this is I think apply a value for individual pixel. And for the attention map, maybe you also have a way to get back from the attention to the original input. That can also serve as a definition of feature importance. And in terms of the connection, I don't know, but at least for the Jackie values used in this example, you can somehow quantify the uncertainty. But if you use attention map, I don't know. And also the attention map only tell you in the middle, for the middle instead of use the label, the output. So maybe the purpose of those like different.
One more question about the hierarchical cluster. You said you pick one feature from each cluster.
Yeah.
But then you said that method doesn't work.
Right.
What is the reason?
I didn't say that method doesn't work. I think that will cause another issue. You lose some predictive power.
But how much you lose, it depends on how correlated the two features are between each node, right?
And also it depends on how you pick the threshold.
Yeah.
So these are also very arbitrary. That like why should you pick certain threshold, and whether the metric for the correlation with metric is reasonable. You use unstable or other correlation metric. Which one will be more reasonable? And you need to make many choices to use these ad hoc messages.
So basically, you think it's ad hoc, but you didn't say it fails.
It can somehow adjust this problem a little bit because you are dropping the feature. So once you drop the correlated features, the remaining feature will less correlate.
Yeah.
Yeah. So you can adjust this problem a little bit. I see.
Firstly, yeah, thanks, Jinhong. I think this is a really cool method.
I guess when you were initially describing this problem of how adding error bars will sort of fix some of these issues, my intuition was just to try like bootstrapping the data set and computing Shapley values, some sort of error bars on the Shapley values using that. I was wondering, firstly, if you've tried that, and secondly, like, is that going to be a lot less computationally efficient than the method that you've proposed, or is the disadvantage more that maybe it doesn't have the same theoretical guarantees?
Oh, yeah, that's a very good question. Another way you can quantify the uncertainty is to bootstrap. And in fact, for the second dedication of this method is that their estimate of importance law bias towards 0.
Okay.
So even in this case, even if you have uncertainty, it is not possible because the point estimate is already like not a good estimate.
Okay.
And yeah, there are ways to construct inference for Shapley value, but these are computationally expensive. Even to estimate this quantity, it would be hard.
Okay, cool. Thanks.
Good. So there's a Zoom question. So does it matter if the distinguished latent variables are not independent while uncorrelated? It is kind of uncorrelated or independent.
Oh,
so my understanding is you try to reach that such that they're independent. So what's happening if
they are not.
but uncorrelated?
Actually, there was a reviewer also asked a similar question. What if the different variables are not independent? So in fact, there are some metrics we can use to quantify whether the coordinate are independent or not. So those I forgot the name, like some Hilbert states independence criteria that you can compute to see the latent variable you get they are independent or not. Yeah, we can kind of have a small for the independence level. Yeah.
Can we all line up? Just we want to get a group photo of us. Yeah.
Can we just move closer? Everyone's hungry, so we after we finish we can go for lunch. Thank you. Okay, everyone. Okay. All right. Thank you for playing. Can I have a big smile from you? Thank you. 1, 2, 3. Bigger, please. All right. Thank you.
Thanks.
Oh, one more. Oh, sorry. Yeah. Biggest. Thanks. Oh, you read my email? Yeah. So fast. Nice to meet you. I'm Alec in IDS.
Nice to meet you. Hello. That's Boris. I'm Alan. So actually, my PhD is in physics, but I'm in IDS. Yeah. Yeah, that's fun. It's a nice.
I don't know. Just stand there, don't laugh. But you tell about
Hello.
Yeah.
Okay, that's really cool, and then you can ask the thing is that because the